Good evening, everyone. Can you hear me well? On the back seats? Yes. Welcome to University of Lincoln. My name is Professor Andrei Zvelindovsky. I'm head of School of Mathematics and Physics, which organizes our public lectures. This is our special Christmas public lecture, Isaac Newton Christmas public lecture, the first face-to-face since pandemic. So perhaps some of you came in our before pandemic times to these lectures. So welcome back. Those who come for the first time, welcome as well. Hope you can enjoy this evening. Small kind of housekeeping. So in case if there is fire alarm, so the exits behind me, but also on far away sides above, above there. The lecture, as you might read, consists of two parts, about half an hour, then break about 20-25 minutes, another 25 half an hour minutes, and with some maybe 10-15 minutes for questions. You have been receiving email that the temperature is a bit cool. As you also might know, here in the news, Lincoln experienced this power cuts kind of every other morning, seems like. So our heating system, in fact, in this very computerized building did not could not cope with this, and it switched off, and the heating provided by this portable heating devices, so will be a bit of extra noise, but I think we just managed to make it reasonably comfortable. So please enjoy your break when it will come. During break will be some music playing, and the music is also, by the way, related to fish and to goldfish in particular, but everything has its own time. I am very happy and honored to welcome here Professor Roos, who is our traditional speaker on all of our Christmas lectures. Those who came for the first time, and those who came already for third, whatever time, will still happy to hear a few lines about Andrei Roos. Andrei Roos earned her PhD from University of Colorado, United States. She has taught in Salisbury University in the United States, University of Minnesota, and University of Oxford here in the United Kingdom. She is currently professor of the History of Science and Medicine at the University of Lincoln. Professor Andrei Roos has been a visiting fellow at All Souls Colleges in Oxford, fellow at the Huntington Library, and John Rylands Fellow of the University of Manchester, and Binecke Fellow at Yale University in the States. Andrei Roos was the recipient of the John S. Thackeray Medal for her work in the history of natural history, and in 2023 she will deliver the Golden Delaunay Medal lecture at the Worshipful Society of Apothecaries of London. She is a fellow of the Linnean Society of London and the Society of Antiquities of London. Andrei Roos is the editor-in-chief of Notes of Records of the Royal Society Journal of the History of Science, author of 10 books and editions, and dozens of journal articles and book chapters. Her recent books include Martin Fox, a Newtonian Antiquity Connoisseur at Oxford University Press, and Goldfish. That's why we are here. Her work has been funded by the National Science Foundation, the Andrew Mellon Foundation, Arts and Humanities Research Council, the British Academy, the Royal Society of London, the Wellcome Trust, the McKnight Foundation, the Society of Authors, and the Lincoln Record Society. And I'll ask her, please join me in warm welcome to Andrei Roos.
Thank you, Andrei, for that lovely introduction, and thank you for coming on such a cold evening. Maybe we can warm up with a little goldfish. We'll try. So, when people are asked what animal they would like to be if they are reincarnated, many respond a dolphin. Those altruistic, smiling, social, and sleek acrobats of the deep. But for me, it would be the humble goldfish. cared for by a winsome child, as we see here, who would call me Cheeto, Goldie, or Bubbles, and provide a reliable drift of fish plates and a spacious aerated aquarium, 25 gallons of sheer tranquility. As a bonus, I would get to be my favorite color of orange and live in a Barbie pink castle, appropriate environs for the oldest ornamental fish in the world. Even Henri Matisse, in his 80th year, claimed he wouldn't mind, he said, turning into a vermilion goldfish. The fish appeared in no less than 9 of his paintings, for the artist a reminder of the sensuality and exoticism of Morocco. It would be a life prosaic, yet glamorous, just like the goldfish itself, an animal that is once ambiguous, liminal, and surprising. Not for this creature does familiarity breed contempt. Rather, we should think of the goldfish as a human cultural artifact created through a millennium of religious reverence and selective breeding for practical purposes, consumerist aims, and aesthetic expression. We will see in this talk that goldfish are world travelers and shifting self-contradictions, rare and common, scientific hero and environmental villain, their relationships with humans often unpredictable. Even the origins of the goldfish are ambiguous. When in the mid-18th century, Carl Linnaeus, the founder of binomial taxonomy, so that's why we're called Homo sapiens, everybody has a double-barreled sobriquet to define them as a species. When Linnaeus gave the goldfish its modern moniker, Carassius auratus, the golden carp, he was not describing the wild single-tailed progenitor, but an exotic twin-tailed individual. But by the 18th century, goldfish were everywhere, even in Sweden. Goldfish had reached the continent as from 1740s onwards, interest in marine zoology grew in Europe. Naturalists like the indefatigable physician, Job Baster, I have to say that name very carefully, you know, bred goldfish in the Netherlands. Baster resided in Zierikzee in Zeeland. It's the least populated area of the Netherlands, consisting of islands and peninsulas, figuratively and literally a backwater. For example, in one of his letters to Linnaeus, Baster wrote, "Nothing ever happens here." Although in 1754 a number of goldfish were in some noblemen's ponds in the Netherlands, they hadn't managed to breed. Baster, however, saved the day for Dutch goldfish. We inherited a garden called the Zonnehof, or the Sun Garden, with trees and 2 ponds. He cultivated a contact in England, and he obtained 12 goldfish. Although these all quickly perished in his garden fish ponds, probably due to the winter cold, maybe like we have today. His efforts the following year were much more successful. In the winter of 1759, he introduced 16 goldfish to his pond, and soon he saw some little fish, 4 to 6 lines long and of a blackish or swarthy color. 6 weeks later, most of them developed silvery or white spots. He recorded his absolute delight at seeing the fry change to silver and gold. He said with such a spectacular splendor that our best gilt pales by comparison. And he observed them under the microscope to see the movement of the viscera so clearly. And he drew their scales, and you can kind of see the scales up here. He even flecked the figures of his fish in gold to emphasize their beauty, and you can see this if you turn the page, it kind of shimmers. He said he recorded the fry's grubby green color that was transformed into shimmering silver or white. He liked seeing the goldfish play and dart in the water much like we do. He recommended the importance of introducing the fish gradually and gently into new ponds rather than just dumping them in, or else the fish would dive to the bottom, afraid to come to the surface and eventually suffocate. He learned to lower a bucket of the fish hanging by a rope gradually into his ponds, letting the fish swim out of their own accord. That's something breeders do today. He noted some of the best food for the fish was a Dutch waffle soaked in water. I think so too. But biology and gastronomy were closely related in other ways. He wrote, I have cooked the largest of the goldfish, and I have eaten them in company with good friends. We tried them with various sauces, but with the so-called egg sauce, they were the tastiest and much better than the common carp. They were much tenderer as some river fish, and they don't have obnoxious bones like the roach or pike. They were as delicious, baked as perch. He was ultimately forgiven for eating his experimental subjects. In 1976, a statue of Baxter made by the Xerxes sculptor Odd Brott was unveiled in front of his residence, the Havenplein, and it shows him here holding a goldfish with a little goldfish in the pond peeping up at him. Now, because I'm such a goldfish geek, I went all the way up to Xerxes, and his former house is now an Airbnb, and I wrote the owners asking if I could have a look around. I think they thought I was insane, but they let me in, and I actually got to see where his laboratory was, so that was a real thrill for me. Despite Baxter's voracious appetite, part of the goldfish's biogeographical success is that they are prolific breeders. They're pre-programmed to spawn when the weather turns warmer, the daylight lengthens, and the water temperature rises to about 19 degrees C. Now, outside of mating season, you can't really tell the difference between a male and a female. But with the advent of spring, the female's abdomen gets rounder, and the males sport these tiny star-like little white tubercles on their pectoral gills and fins. A lot of people who have goldfish think that they're infected with something, and really it's just the males are kind of getting randy and they want to have some little goldfish babies. But where did this bacon fish ultimately come from? That, surprisingly, is a matter of scientific debate and investigation. We know the goldfish is native to China, particularly the southern Amur River Basin and Korea, and we think it was domesticated in China about 1,000 years ago, specifically southern China and the Yangtze. For those molecular geneticists and fish fanciers out there, we think they may have originated from a hybrid of the red Crucian carp and the common carp. In ancient China, the wild goldfish, or qi, more correctly, qi yi, was colored dolphin gray or olive green and had a deep and more lateral body. Our common goldfish are a little bit rounder. It reached a size of 14 inches and a body mass of about 2 pounds, so a little bigger than we think of as goldfish. At some point in the distant past, gold and redfish appeared among the gray qi due to a genetic mutation. Qi are normally this battleship gray because of pigment cells that are called melanophores. They're the same type of things that we have when we get a tan. But they also have two other kinds of pigment cells that are called erythrophores and xanthophores that color them red and gold. At some point, we think a rare mutation occurred that suppressed the gray pigment cells and allowed the red and gold ones to express themselves. Because they have a molecule in their scales, a nucleotide called guanine, the scales are shiny, so they sort of shimmer when they swim. Now, some ancient Chinese authors attach a supernatural significance to these very strangely colored fish, regarding them as sacred. The transformation indeed must have been miraculous, going from this grubby gray to this beautiful gold. As the Chinese word for fish is pronounced very similarly, but in a different tone to the word for wealth, goldfish over time became symbols of prosperity in China, which may have accounted for their sacred status. And it's really typical in the Chinese New Year to see a child holding a large goldfish and a lotus flower, and that symbolizes abundance of gold and harmony. And these are little money envelopes that you'll see given on Chinese New Year. People give each other gifts. And you can see this was the year of the bull. You see the small child holding the goldfish and stamping out the year of the crab. So goldfish and wealth are synonymous together. Buddhist monks, we think, encouraged the proliferation of goldfish because they thought they were sacred. They kept them in special ponds as religious practice to cultivate compassion and earn merit. Why was that? Well, if you are a goldfish, you are extremely, extremely conspicuous to an overflying heron or bird of prey, and they'll come nab you, as any of you have tried to keep fish ponds away from heron. And so we think that this is how goldfish started to interbreed and proliferate. And also, it was considered dangerous to eat them. In AD 1223, it was reported in the spring in Chichen, one could see gold and silver chi of the most delicious taste. But it is said they are so mysterious that fishing boats approaching them often turn upside down. So don't eat goldfish. In modern Buddhism, goldfish are also actors in another religious ritual called Fang Sheng, or mercy release. That dates back to the 3rd century. It's governed by spontaneous acts of devotion, where animals that are raised or caught primarily for sale to pious individuals are actually released into the wild. In Taiwan alone, 200 million wild animals each year are used in this practice. Not only goldfish, but monkeys, birds, and baby turtles. The latter sold in markets for cooking or releasing. Now, whether the goldfish is released into the environment for religious reasons or just as unwanted pets, it causes untold environmental catastrophes, and it's actually banned here in Britain and in America. The goldfish's extreme hardiness and ability to breed prolifically overwhelms ecosystems and kills off other native species. So they're so good for karma, but so bad for other fish. A sacred menace is the goldfish. Goldfish that are flushed down the toilet or dumped in lakes and fishermen use them as bait can achieve a density of up to 17,000 fish an acre because the females can produce 40,000 eggs a year. They're also omnivores. They eat anything. They don't have a stomach, so they don't store food very well. So they graze during the day on plants, scale, snails, insects, crustaceans. They decimate native frog populations by eating tadpoles. They snack on the eggs and larvae of long-toed salamanders. They also poop a lot, and that causes algal growth in lakes, and it muddies the water, destroying the feeding and refuge habitats of other fish. They've been listed as an aquatic nuisance, in fact, in the United States and Australia. To give you an idea, that's a goldfish. They're carp. They can actually get to be this big, right? I mean, that's kind of scary. That isn't just a little guy in the bowl. In 2015, more than 3,000 goldfish took over Teller Lake in Boulder, Colorado, after someone dumped a handful of unwanted pets. It made international news. It was on Comedy Central's Midnight program. Host Chris Hardwick called it a revolutionary goldfish blankety-blank fest, noting, "These guys are really making the most out of not dying in a toilet. Good for them." On last report, the Fisheries Commission planned to electroshock the goldfish to get them to float to the surface and then donate them to a raptor rehabilitation center as feed. You know, it's really happy eagles there. But the planned execution at Teller Lake never took place. And why was that? These guys, Mother Nature came to the rescue. A flock of very hungry American white pelicans flew over Teller Lake, looked down and said, "Ooh, a snack," and they absolutely ate and gobbled every one of those up. So successful were the pelicans that the state of Colorado considered actually using strategic placement of rehabilitated pelicans to solve this problem. Now, need I give the impression that goldfish are total villains? They're also heroes to science, and sometimes long-suffering ones. If you were to happen to type in the word goldfish into the Bodleian Library database, nobody does that but me, right? Absolutely not. You will get 40,000 results of scientific papers that use goldfish as experimental models. In their sensory organs, goldfish are a lot like us. They make them ideal experimental models that are cheap and easily obtainable. They're smart enough to be trainable in studies in visual perception and cognition. They perceive the same colors as humans. And remember when I said they have pigment cells in the melanophores like humans do? They produce pigment response to light. So in some ways, they can kind of get a tan. Maybe that's why the goldfish cracker logo there wears sunglasses, right? Their ubiquity in scientific research led to the realization at Harvard Medical School in the 60s that they even could be used to study alcoholism. Their blood alcohol levels come into equilibrium with the water in which they swim. So if you want to measure the amount of alcohol in the blood of a goldfish, you just need to really measure the amount of alcohol in the tank. They were subjected to tests of memory after being exposed to different kinds of alcohols in a maze. And fish with bourbon in the water learn more poorly than fish with vodka in the water. Now, why was that? We think it's because that bourbon has congeners, they're particular organic compounds, esters and aldehyde, and this must interfere with memory retention. After continuous exposure to alcohol, their ability to learn is unaffected by higher levels in the water, so they actually develop alcohol tolerance, just like we as humans do. It was also recently discovered that goldfish have an alternative metabolic pathway to make alcohol. When we're in the low oxygen environment, we switch to something called anaerobic respiration, yeah? And that makes lactic acid in our muscles. That's why when runners are running out of oxygen, they get the burn in the back of their legs, and we can't sustain that respiration very long at all. Goldfish do something a little different. Instead of making lactic acid as a byproduct of metabolism in the low oxygen environment, for instance, when they go to the bottom of a pond in the winter, they make ethanol, and they expel the excess booze from their gills. Now, I mean, I think there's got to be an easier way to make whiskey, right? This really contributes to their hardiness and their ability to outcompete other species. As goldfish are naturally exposed to this higher ethanol concentration, they are seen as model systems for the study of molecular mechanisms protecting them against chronic alcohol exposure. In other words, they think they might hold the key to mitigating the adverse effects of chronic alcoholism, particularly as they spend the winters with a blood alcohol level that exceeds the drunk driving limit. As we use goldfish and their organs as experimental models so extensively, it's also maybe discomforting to note that they're very intelligent. This idea of a goldfish memory is completely wrong. They actually remember quite well. It's known anecdotally that goldfish will be more active in anticipation of feeding time. They'll respond to you. They know when you're going to feed them. But this has been tested scientifically. They can learn to press a lever at a particular time of day to obtain food. They cluster around the lever for an hour that it's operated. And when the food dispensers are made inactive, the fish still remembered meal times for 2 days and then stop pressing the lever. So they can tell time, and they can remember through associative learning. It seems the goldfish is ubiquitous, with ambiguous status in its relationship to humans. At times, a troubling environmental menace that stirs up the waters. At other times, a useful experimental model, sometimes of little value, a carnival prize. Why elsewhere is considered an uncomfortably smart little creature demonstrating incredible evolutionary adaptation to its habitat. It's a contradiction, not just in the sciences, but also in the arts, and it can bring great luck or terrible tragedy. I'm going to conclude this talk by telling you a fairy tale. It is by Alexander Pushkin. It was published in 1833, and it's called The Fisherman and the Fish, and this is a stamp that was made to commemorate this fairy tale and Pushkin. For Pushkin, the goldfish was a hero and villain all at once as well. The story goes like this. Once upon a time, there was a peasant, and he was living in a mud hut, and he was just eking out his living as a fisherman. He had a poor old wife. His wife spun cloth to get by, and they couldn't even repair their water trough. And one time he was fishing in a very calm sea, and he caught a tiny little goldfish, maybe something like that. And the goldfish was struggling in the net. Much to his surprise, though, this fish spoke in a very high, frightened voice. Please don't eat me. Please don't capture me. I'll give you any wish you want if you set me free. And the fisherman let the fish go, and he said very kindly, God bless you, golden fish. I don't need anything from you. Swim where you wish. So he thinks he's done his good deed for the day, right? He gets home to his wife, and she listens to this story. And she says, you're an idiot. You could have asked him for anything you wanted. At the very least, you could have gotten me a new watering trough, because ours is broken. So with some trepidation, he goes back to the shore. He approaches the fish. He bows. He apologizes for his demanding wife. The fish comforted him, and he said, could I have a trough? No problem. He gets home, trough appears, but one thing he noticed when he left is the sea was just a tiny bit more stormy. Now, the wife's demands increasingly escalated to a new frying pan, which was granted, a new house, which was granted by the fish, and when the goldfish's gift of a pleasant, whitewashed little cottage wasn't good enough, she demanded to be a noblewoman, and then a mighty czarina with a sable jacket, and pearls, and fine red boots. Sitting on her throne and surrounded by servants, she banished her husband to go live in the stables. Boy, the sea grows more stormy, the sky is growing dark and troubled. Finally, his recently ennobled wife, insane with power, made her last request to be empress of all the land and the sea. Now there's thunder and lightning, and there's giant waves crashing on the shore. And the fisherman had to yell above the noise to make his request of the little fish. This time she simply made no reply, and she swam away. The fisherman returned home to find his mud hut, his poor wife sitting outside it, and the broken trough. This tale is also a parable, it seems, for our relationship with our own goldfish. Through their habitation with us, goldfish have innocently unleashed environmental catastrophe, but that's because we've treated them like a disposable commodity or used them as cheap bait without recognizing their true value and role in the natural world. Perhaps when we see their magical qualities of beauty, of grace, of evolutionary adaptation, and of intelligence, we can respect Carassius auritus in its own right. Thank you.
Thank you. Now we have an interval. Please enjoy drinks and some music outside, which is also related to goldfish.
I have really great pleasure in introducing my colleague and friend, Andrei Zvelindovsky. He's founding head of School of Mathematics and Physics and professor of computational and theoretical physics. Andrei received his PhD in 1993 in the dynamics of complex fluids from the Department of Theoretical Physics at Odessa National University, Ukraine, where he continued in research and academic posts. From 1997, he worked in research posts at chemistry departments in the universities of Groningen and Leiden in the Netherlands. In September 2004, he joined the University of Central Lancashire in Preston as a senior lecturer and founded a computational physics group, which attracted funding from EPSRC and EU. He became a reader in 2006 and a professor of computational and theoretical physics in 2009. And he wanted me to add that two of his PhD students got Institute of Physics annual PhD thesis prizes in computational physics. And this is basically for the best PhD thesis in computational physics in the UK. And I think he's probably the only UK academic with such prizes for his students twice. So it's not very surprising that in September 2014, Andrei became the founding head of Lincoln School of Mathematics and Physics, where we greatly value him as a colleague and a researcher and scholar. I'd like to introduce Andrei and his presentation, Physics Taught by Goldfish. Andrei?
Thank you very much, Anna-Marie, for a nice introduction. Just would like to check if on back row seats you can hear me well, right? And also, some people thought that light was a little bit dark, so the faces, so can you see my face? I hope it will be not the only amusement. I just kind of to add to this introduction, not that I want to tell much, but there's two PG students mentioned who won the prize. One of those students got prize in my previous institution in Preston, and one here in Lincoln, 10 years apart. And in fact, the second one was co-supervised with the first one. And the first one now is also associate professor here in Lincoln. And now we will proceed to the difficult part of our evening, because you know, the tea and coffee you had, just nothing is for free. Yeah, now you need to learn a bit of hard stuff, physics, and I hope you found a pen and a paper on your desk for end of lecture exam. Did you find? Physics taught by goldfish. We've heard from Andrei Roos a fascinating story of this wonderful, beautiful creature, sometimes misused, sometimes also kind of would be nature hazard. What kind of physics thoughts Professor Goldfish can give to us? A couple of examples, couple of lessons we'll try to learn this night. Lesson number 1, it's about optics, and it's about invisible fish. Some of you might remember this fish ball aquariums, which in fact not recommended anymore due to modern regulations, but some people apparently still have. I'll just play this short video, and as video goes, you will see that one of the fishes will go around corner and will disappear almost entirely for a tiny bit and then reappear again. Of course, everyone who had the goldfish ball saw this phenomenon. And of course, yeah, this is some physics probably inside, or some miracle. So let's see which actually is happening. We know from physics, when the light travels in one medium, then it approaches another medium, one being air, another being water or glass, it deviates from the original path. And then it also can reflect from surfaces, but this deviation from original paths is what is important for our story now. We can check it in every kitchen, so this is what I did in the morning. I performed a very sophisticated experiment. I took a glass of water, and before drinking it, I put a spoon there, and then what you see, the spoon has one handle, but two ends, depending if you look from a surface of water or from a glass. And this is real. It's not because I had some beer in the evening. It's really, you see that. The phenomenon is precisely due to this deviation of light after crossing the surface, if two materials are different. We can perform another experiment, look in the same glass, another spoon, or you can use the same, and you can look on the spoon from a bottom, so kind of keep a glass on the working table and look. What you observe that the surface of air and water becoming as mirror, as a surface of liquid of mercury, and you have a perfect image of your spoon in that area, and moreover, you won't see, for instance, my fingers through this surface. They're invisible from there. This phenomenon called total internal reflection. So what exactly happening here? Now we have water, like here, and air above, and the light goes from the water towards the surface of air. As it reaches that, it goes into the air by changing its angle, because the rule is angle will be always changed once light crosses the interface. And it bends and it bends. The larger the angle is, the more it bends, till will be certain angle which we call critical, when it bends so much that it goes parallel to the surface of water. And that means no light goes into the air with angles larger than those. This is what we see in our kitchen experiment. This is for flat surface. Scientists in China, they, of course, you know, goldfish come from China, so it should be scientists in China who resolve this puzzle. They actually thought, what will happen for not flat surface, but for a fish ball, for curved surface? And the result by Zhu and Shi was published in a journal Physics Teacher to bring it to a wider audience. So they performed the same drawings as I've done for flat surface, but for curved surface. And what they found that you actually can have two positions where angle going from this point to the surface of glass has the same value with a tangent to the surface. Two values. They also could prove, with help of beautiful Greek geometry, that there are indeed exist all these two angles. And that is because there is a maximum value of angle. And that maximum they geometrically proved will be when you have a line drawn perpendicular to a line connecting center with line where fish is. If this is maximum, on both sides will be lower values. So one maximum on both sides, left and right, will be two lower values. This is how they prove that there are two values. So there are two values for critical angle for curved surface, not one like for flat. And therefore will be this blind spot where will be no light coming, and therefore if we position our eye there, we won't see the fish. And of course our cat perfectly knows that physics. For that cat knows if it will look from a side, fish can hide, but it cannot hide if the surface is flat. So fish knows this lesson cat knows this lesson very well. We didn't finish yet with lesson. I always like history, and somehow you see I jump here centuries back to our Bishop of Lincoln, Robert Grotest, who wrote a book about rainbow. 1,000 years old phenomenon. People tried to resolve. Bishop Grotest did not solve the problem. People after him finally solved it, and rainbow happens when the light comes to the spherical droplet, splits them in different parts. This is also what Newton already knew, and then it creates multitude of colors. And you can calculate precisely angles when it happens. Our fishbowl is also sphere. So another scientist, this time in Brazil, they revisited findings of scientists in China by putting, instead of fish, they did not want to experiment on poor animal, they put just simple light. It's good enough, light shines. When we see no light, here, this is blind spot. When we see light, this is where light goes. What they found in this experiment that, yes, there is a blind spot, as Chinese scientists predicted, but the boundaries looks different. One boundary is kind of a little bit sharpish and maybe colored, and another diffused. So they performed calculations, and they performed more experiments, and they indeed found that the reason why boundaries are different because there is a rainbow effect on the top of that Greek geometry which I described before. So quite complicated lesson just from something simple as a fish bowl. Now we look at lesson number 2, and it looks also simple. It's Archimedes' principle. In this few seconds of video, we observe highly inbred telescope goldfish, and we see a poor animal likes to sweep upside down. So why that happens? Why the fish loses stability? So maybe it's the same as stability of a boat on the sea. In fact, we immediately understand not entirely, because for the boat, the part which pushes boat from the water is the only part which is under the water level. For the fish, the story is different. Fish is entirely in the water, so the story should be somewhat different. How different? So we want to look how the stability of fish can be explained. As physicists, I like simple models. This is my goldfish, drawn very carefully, many hours of work. And you know, what else I can say about goldfish? We know that goldfish inside has various parts, and an important part, as you see here, is the swim bladder. It's dark on the X-ray because it consists of air, so X-ray is not kind of affected by that. So this is my, again, simple model. I'm only interested in the swim bladder, which is full of air, and the rest, which could be muscles, bone, and whatever. There are two physical forces acting on the fish to consider. One is gravity. Gravity penetrates all matter doesn't matter, air, muscle, skeleton, all through the fish. It feels all the structure inside. If the structure is lighter, less gravity feels. If structure is denser, will be more gravity effect. As a result of that, will be center of mass, center of gravity, a bit of above of this pocket of air, which is swim bladder, somewhere there. Another force is Archimedes force, or buoyant force, and that has totally different type of action. It acts as a pressure on the surface of a fish, and it's larger at the bottom because water pressure larger, and it's lighter at the top. It doesn't feel what is inside the structure of the fish. It only feels its total volume, total shape of the fish. As a result, the center where that force can be applied is not in the center of mass, but in the center of buoyancy. It's like geometric center, or in other words, the center of displaced water by the body of the fish. As we have shown here, these 2 points are not the same. For majority of fish, one would be a little bit above than another, moreover, like this. So the gravity will be above and buoyant one a bit below, creating rotational force. This is why fish need to use these flippers, which are so skillfully kind of displayed here to sustain stability. And highly inbred goldfish would have deformed part of bodies, and therefore what is put genetically into the mechanics of things would not fit the structure of deformed swim bladder, and that poor animal then have life sometimes a little bit upside down. Now, okay, we now discussed why fish stable or unstable, but what about the most important part of the fish? But why does it swim at all? Obviously, it swims because it has fins, right? It's again, spent hours of work trying to show you how exactly it does. But if you look carefully on this cartoon, you actually notice that while it moves things up, it does it slow, and then it moves down, it does it fast. That is because, of course, it's very clever kind of fish here. It uses inertia, but we need to say a few more words about. So things are used by fish, they're used by humans, so we grow them usually from our feet, so this is where we have our things. And there are creatures much smaller, which don't have really kind of precisely things, but they have antennas which looks a little bit like our hands with almost like fingers. From point of view of physicists, they're as good as these bars here. They try to make these movements. These creatures, Daphnia, can swim quite okay, not entirely precisely, but still quite okay. So again, maybe it's exactly the same as the ancient ship with oars, same mechanism. We immediately understand, again, not exactly, because oars are moving in the air and in the water. There is symmetry breaking there of different medium. Fish is, again, completely in the water, so it cannot be the same analogy. Something is different going on. And there's no other way around, so we need to go to difficult stuff. Now we'll show the second most difficult equation of physics, and that is this. And of course, we need to go carefully through every single symbol. However, if you don't believe me, this is a very difficult equation. I hope I can convince you that that gentleman used that theory of fluid dynamics in his PhD thesis. He received Nobel Prize, of course, but not for his PhD thesis. He has several other papers written in his miraculous year, but his PhD thesis is not mentioned there. However, it was written in the same time, and miraculous, and it has mistake. So definitely that equation is difficult. If Einstein made mistake, which took him 6 years to correct, moreover, then someone student pointed to him that there is mistake, and he still couldn't understand it. He wrote letters, and then finally everything was done, it was correct. So it is a difficult equation. I mentioned it's second most difficult. It used to be first, but then Einstein invented general relativity, and that occupies the first most difficult equation in physics. Right, so let's go into detail, but no, we actually don't need to go to whole detail. We can look on something much simpler, which is so-called Reynolds number, which in fact puts the most important part of that difficult equation in a somewhat simpler terms, so-called dimensionality analysis. It connects three letters: speed, characteristic speed of movement, size of the object which moves, and so-called kinematic viscosity, which is proportional to viscosity. And for water, viscosity is 0.01 centimeter squared per second. For different objects, we just need to check size and velocity. And usually, creatures with things swim roughly own length per second. For instance, humans, you know, of course, every human is about 2 meters or above, so let's put 2 meters. And roughly speed can swim own length in second. Goldfish also can do a little bit faster, a little bit slower. It depends if they have dinner or not. So can swim roughly own size. Daphne, which doesn't swim very precisely, however, it can do it actually a little bit better, several own lengths. It was measured in various experiments. And of course, you can do it at home when you feed Daphne to your goldfish. Then it really tries to do several lengths of, So if you calculate Reynolds number, this is what you find: 4 million for humans, 2,500 that value, and it's dimensionless because no units, for goldfish, and 30 for Daphne. Reynolds number roughly tells what is more important: inertia, and this is where we try to move things faster in one direction and slow in another direction, or viscosity. And if it's above above 1, then inertia prevails, and then things work like this. If it's less than 1, then viscosity prevails, and this is why we cannot use the same mechanism swimming, for instance, in honey. That particular kind of work was specifically started by Edward Mills Purcell in his classical now article, Love at Low Reynolds Number. Edward Purcell, who 25 years before that date got Nobel Prize, but for something different, for discovery of nuclear magnetic resonance. So very, very kind of a renowned physicist. So what to do? We cannot use things if we are smaller than Daphne. Nature, of course, knows physics very well, so they found solution. For bacteria, in this case E. coli, you see there are no things here. There are all kind of flagella which bacteria use to swim, totally different mechanism. It does it because Reynolds number is extremely small, and swimming using inertia won't work. But nature knows this physics very well. Now we move to our last lesson. And some of you might visit it in the past, before pandemic, a wonderful Japanese garden near Lincoln. If anyone visited Japanese garden near Lincoln? Yeah. Unfortunately, as I kind of check in every kind of one upon a time, it's still closed now, till further notice. That is absolutely fantastic place where you can enjoy a real Japanese landscape, because the owner actually a Japanese gentleman who spent 40 years making that garden. And inside the garden there is a pond with substantial school of goldfish, koi fish. Koi fish, as some other fishes, just a second, I need to does something like this. It's schools, so it can create schools. Of course, the fish which is in front, near the gentleman which gives food, it's C, basically the gentleman. However, fish which is behind, they see only fish near to them. And they still form this very nice and coherent pattern, moving all together. And sometimes they joined also by other creatures from different families, so doing the same kind of, there is some other creature thinks also I'm fish, and really just want a little bit of food. So, of course, we don't know quite why and how fish does it, but we can try to create, again, simple models and experiment with this model. So I propose here a model. That model is not mine. That was proposed by Hungarian physicist Vicek some years back. So consider two animals swimming. If they're far from each other, they don't see each other, they swim each one in their own direction. So one swims here, another swims there. But if they happen to be near each other, they see each other, and they, we hope, want to swim together in the same direction. So how we can make it in a language of kind of mathematics, which is language of physics. We now consider just the direction of movements. So these two arrows depict where each fish would swim, and then we want to introduce a rule how we tell that they will now swim together. That rule can be different. A simplest one, just summing up these two arrows together, mathematically. How we do that? We take one arrow, we place it on the top of another, and then connect their ends, and this will be a new direction of swim for each of the fish, like this. And now both of these fish will swim together in the same direction. This is, of course, a very simple rule, and you can experiment, you can make other rules, then compare to what you observe, compare not only to the fish as goldfish, but other fish, but also to other animals. This type of collective schooling is also known in birds like flocking, and known in insects and other creatures. And in fact, the science there are becoming quite rich. With my collaborators from Ukraine, Netherlands, and Norway, we looked at, by starting from such a simple rules, we end up in a very beautiful area of constraint dynamics, and then we can observe transitions of spontaneous formation of these flocks moving, breaking them, forming vortices, and so forth. Moreover, because the original rules are so simple mathematically, many people can get involved and try a bit of this research themselves. And in fact, I want to finish my mini course here with this video made by my nephew, who is sitting somewhere now in the audience over there. Last Christmas, I visited him in Ukraine, and in some evenings, he just made this computer simulations using that mathematical model I showed you, but made it actually more elaborate. For instance, he introduced some hungry fish. So these are yellow ones as a goldfish, and they can form schools. You see, they form large schools. Schools come together, swim together, and there is some predator here, and it can put a panic attack in some fish, and can scare the fish and kind of move them together. And this is what everyone, in fact, can do. So start with simple models, create dynamical patterns, study behavior, and in that step by step try to understand complex dynamics behavior of various animals, including goldfish. And with that, I'd like to say a few acknowledgements. First of all, acknowledgement goes to my own goldfish, which very comfortably lives under the ice in a pond in my garden. And in fact, when I say comfortably, it's true. Ice is in the top, and there is another physics involved, but possibly for another lecture. And then also to my nephew, who now studied in UTC, so he's 14 years old, so that simulation he done at 13 years old. So he moved from Ukraine, joined study in UTC, and was very kind to help me with putting some of animations in this presentation. And with that, we finished. Thank you very much for listening. Now we have some time for questions, so we have plenty of time, but if you would like to, if you want to leave, so don't be shy, you always can leave, but Anna-Marie, Roos, and myself are very happy to answer any questions you might have. We have Aaron here to help with microphone.
No one's holding me.
Where's the mic?
Mic has disappeared somewhere.
Where's the microphone? Oh, no. Oh, there it is. How many physicists does it take to turn on a microphone?
I'm just using your one. Is it working? Yeah.
Yay.
When the goldfish school together, does that change the Reynolds number? When the goldfish are schooling together, does it effectively change the Reynolds number?
That is actually a very good question, right? A typical answer. That PhD thesis of Einstein, which I mentioned to you, was about, the title would have new ways of calculating Avogadro number. But he studied how viscosity would change if he would add spheres, solid spheres, into the fluid. And he found, yes, it's viscosity is being changed. If viscosity is changed, Reynolds number would change. That was just for Einstein work. Okay, originally he found he put a mistaken formula. It was changing but wrong. If he put fish there, we always can approximate fish by just sphere, as I did. So yes, viscosity will change, but in a different manner than just spherical particle which doesn't move. And I don't know actually the works where such calculations been precisely performed. The research on this schooling of objects is quite recent, and it's called even a new name now, so called active matter. So yes, so that could be still topic which people did not find yet answer.
Just one question. What is the species of goldfish that you used to get in the little plastic bags in the fun fairs?
That's Carassius auratus. That's the species, the golden carp. Now, you can get many, many different varieties of goldfish. There's probably, I think there's actually a British Goldfish Association, which you might expect, and they actually there's different what they call varieties from that one species, but they're all Carassius auratus. That particular fish that you get at the fun fair is actually based, if you can believe it, on a United States model of goldfish. In the 19th century, the American ambassador to Japan brought back a series of goldfish and bred them to a particular standard and to mark the creation of the U.S. Department of Fisheries and Wildlife. Now it's the USDA, and to spread the relationship that the United States have with Japan. You could write your congressperson, and you could actually get a free goldfish in a bowl. So that variety you see there is one of the most common ones, and it's based on the U.S. standards. Americans also developed one called the Comet, which has got multicolored and is a little bit elongated. The Chinese varieties of goldfish tend to be larger and more colorful. The Japanese variety of goldfish are more appreciated to be seen top down, and they're almost more rectangular in shape. They're supposed to be emulating sumo wrestlers, very compact, muscular swimmers. So you look at them from the top down, where the Chinese like to look at them as we do, side on. So, but they're all Coracia serratus.
You were explaining, if I understood it correctly, that the position of the swim bladder in goldfish causes it to be unstable, and it therefore needs to engage in fin action in order to stay upright. Yes?
Basically, you know, you might observe when fish dies, right? It goes upside down. And it goes upside down because the majority of fish, the center of gravity and buoyancy, one is above another. So it intrinsically would rotate fish upside down. Not to do it, fish uses things to stay upright. They're similar, like I would, you know, if I would stop being alive, I would fall. I use my muscles to actually stay upright.
So my question is, what does the goldfish do when it is asleep, or do they not sleep?
This is for Anna-Marie.
They do sleep. They sleep with their eyes open. So it's like eyes wide shut, sort of like, they look like they're staring at you, but they do sleep. And they're fairly light sleepers, as you can imagine. A lot of animals that are prey animals are light sleepers. And they actually don't have ears. They have lateral lines in their body which detect vibrations, and that can move them towards or away different things, but they do sleep with their eyes wide open, yeah.
And of course, this torque or rotation force which needed, it isn't something very large. So the fish doesn't need like enormous kind of movements unless it's ill to stay in normal position. So if you look, if I look on my fish, which is almost frozen, no, it's not frozen. Even while sleeping, it occasionally does something with things. This is kind of to have this tiny balance. The small force there, so if fish is healthy, all these organs such position that it's just a tiny kind of rotational torque there and the tiny movements enough to stay upright. If it's highly inbred fish, all the organs are deformed and the things are designed by genetics for different kind of, you know, they not enough to keep balance perfectly. And that's why, you know, some fish lives upside down, and I think they thought that some fish is even special species, right?
Yeah, when news of Japanese goldfish first reached the West, I actually found a manual where they showed an upside down fish and they classified it as a different variety. They didn't realize it was sick. I have it somewhere in illustration in a book I wrote about them, but yeah, a little bit of knowledge was needed about the internal anatomy. Other ways they breed the fish, they can get very round. They also can breed telescope fish, which have very large eyes. So they've been highly subject to artificial selection by humankind.
Thinking of the swim bladder in goldfish, and any other fish for that matter, what's the evolutionary advantage of having to be basically unstable?
If you look at original wild type fish, they're generally much more elongated, and there's more room for the organs. And actually, it's a pretty efficient mechanism. You remember when Andrei was saying how even when the fish is asleep, it just needs to make a tiny correction. It's only when we muck around with nature's design of a nice elongated balanced fish and we make it more round that we get into trouble, and the fish has to work a lot harder. So I'd say evolutionarily, it's a pretty good design. I actually think the goldfish is one of the most successful fish species out there, just because it's an omnivore, it's very hardy, it can interbreed with other varieties, it can survive extreme temperatures, and it can outcompete other species. It's almost too successful, judging by its biogeographical range.
Thank you.
Thank you. I'm just wondering if there's some kind of mathematical expression of the transition from the schooling instinct and then going into a bait ball when they're being attacked by a predator.
We don't have yet results for the predator model to that degree. In the papers which I showed, we discussed a spontaneous transition to a circular movement, which is observed not necessarily only in fish, but in several other species, like dead circle of ants, for instance. When they suddenly start to move in a circle with seems no obvious reason till they all die. And obviously, nobody wants to die, even ants. Definitely there was something else going on. We look how this type of transition could happen. With predators, it's still very much project in progress. So I hope that my nephew finishes A levels. Perhaps he will write that for me.
Hi, I'm training fish as part of the active animal behaviour, and I'm using positive reinforcement, but as a secondary reinforcer, I have a choice of using a light source or tapping the tank. So I feel like those would have some pros and cons in terms of like migration through the lateral lines, or I was wondering how the fish would perceive the light, if it's sensitive to scales moving.
I think you'd get a stronger result by tapping and something that would be more reinforceable. After the talk, if you give me your email address, I would put you in touch with, I think she's at Rockefeller University. She's done a tremendous amount of stuff with reinforcement in fish to the point where they've learned to recognize quantity and shape. And she's got some different techniques for that. So I'll talk to you afterwards and we'll exchange information. But I'm guessing that the tapping is going to be better, but she'll know precisely. Okay?
I was interested to see the modelling you done at the schools. What it did remind me of was something I saw some time ago. And when we talk about animals, we should be talking about ourselves, because it is actually modelling crowd behaviour as well. Just an observation, not really a question. But
So the type of schooling behavior of fish I briefly mentioned. So it's one of examples of collective movement of so-called self-propelling particles, which could be birds, humans, cars, in large quantities. And they exhibit various very fascinating phenomena. Most fascinating phenomena, of course, when you drive to work and then you're stuck in a traffic jam, that you move 2 meters and then move and then again 2 meters and then stuck, and you think, why everyone cannot just move at one constant but slow speed without this constantly stop and go. Apparently, physics or whatever works in such way that tiny deviation even of speed will result in these waves of movement. This is just for cars. And lots of this kind of phenomena, people found they have very simple kind of behavior at a scale of one kind of species. Like if I'm driving, it's very simple. I just push gas or brake, kind of thing, just these two. But then cars has these collective waves in the traffic jam. Fish, if it just uses this alignment, it creates schools. It creates fish balls if it's mackerel. Bees create waves on the surface of bee kind of I don't know how it's called.
Colonies.
Colonies to repel. We think to repel a predator. We not quite understand how these waves even propagate, because it's not like every bee has mobile phone and tell each other, okay, now we stop. So we try in this active metaphysics, we trying to, with small bits to understand, because not really we know what is inside the brain of goldfish, what exactly is thinking about. We try to guess and then create a model and then predict, and then biologists, maybe they can have another step, maybe actually can tell us one day what fish actually thinks.
Thank you. You reminded me of a model I tried to do a few years ago. On Burton Road, there used to be, this was before the bypass, there used to be quite a long tailback right from the bypass bridge all along to the roundabout on the top of Yarborough Hill. And it was, I thought about it's the principle that we were just talking about, that a sort of long compressional wave, and each car was a particle in it. So I tried to get the evidence for that by building a little Arduino-based GPS data logger. And then you could see the compression as it was plotted out in Python. So it was only a little bit, and it reminded me of what you can do with a slinky spring, because we're all particles in a big system. Right, thank you.
Thank you. Yep.
On the dynamics side, if you've got a school of fish, isn't there like an intellectual decision-making process going on in addition to the particle form?
That is again an interesting question. I have a part of a talk about goldfish. I have another kind of talk where I talk only about the schooling and flocking, in fact. And as a part of that talk, I actually tell that my own fascination of the topic came from a science fiction novel by Stanislav Lem, Polish writer, who has a novel written in, I believe, 1964 called Invincible, where he puts that creatures, which metal kind of small metal robots having one-two functions, communicate with each other, no particular much brain. They create in large quantities a cloud which will have a collective brain function. That was his science fiction novel, so maybe there is something there, but as to my knowledge, science has not yet reached that level.
I think there's a study that showed that you could, when birds fly in V formation, the leading one is doing the most work, and the ones they're in the V formation, so the slipstream from the front wings helps them go forward for the ones behind by taking turns, apparently. Would that be true of the schools of fish as well? The slipstream would help the viscosity or reduce the R a little bit, or increase it, so that they flow better.
It definitely will, yes, in triangles, birds flying, yes, that phenomenon was studied. Definitely when fish, whatever kind of, it's important to also realize what purpose of that school is. Sometimes maybe purpose just to get food, but maybe purpose long migration or a fish ball to repel predator. As fish swims in water, that Navier-Stokes equation, which I showed, will always play some role, and therefore, yes, it will be. What role it will play, I don't think we yet know to full extent.
Presumably it changes with depth as water as well, so there will be a gradient from the surface down to the depths of viscosity.
Water viscosity doesn't change that much even through the kilometers of ocean. It only changes with a bit of salinity, but normally fish which they live in kind of limited, as to my knowledge, range. So if it's a deep fish, it's actually mostly there. If it's on the surface, mostly there. So there's hardly any fish which would be alive and moving from depths and experience these enormous gradients of salinity, because there's other bits coming, osmotic pressure and stuff. So I think basically such fish maybe either don't exist yet or not yet created.
Yeah, I mean, fish. There's a lot of things that determine where a fish lives in the ocean. It's availability of food, salinity, ability to withstand temperature, oxygen level, light level. That's why biology has a lot of variables, and that's why we're still figuring things out. I think we have time for one more question, and then we're going to wrap up.
Regarding traffic jams, a Buddhist once told me that don't ever get angry with the traffic jam, remember you are the traffic jam, which I thought was quite good advice. But with regards to the question, probably for Andrei, I suspect, why do we think that goldfish have short memories? Where does that idea come from?
That's a really good question. I think it was because goldfish have been one of the most commodified animals on the planet. They became almost bred in industrial quantities in the 19th century when the technology arose to make pressed glass bowls. You didn't have to have expensive plate glass to do aquariums. Their popularity as pets took off, so much so there were itinerant goldfish sellers in London that would go around to houses, and it was also sort of a fad for chinoiserie and things of the East. And then, of course, in the United States, these huge farms arose in the Midwest, like Grassy Forks in Iowa, Indiana, that just had hectares of goldfish ponds, and they were sold as loss leaders. You buy a sack of flour, you get a goldfish. And even Depression era people from Oklahoma had goldfish that they would get, and they were a very common pet. And I think because they were so commodified and so ubiquitous, and actually because people didn't know how to take care of them, so short-lived, nobody bothered to really understand them to any kind of level until scientists looked at those qualities and said, oh wow, what a good experimental model, and then they were surprised how smart they are. So if somebody tells you you have a goldfish memory, you say, thank you for the compliment. All right, it's been a real pleasure to speak to you all today. I hope you learned a little bit about the history and the physics of the goldfish, and we really appreciate you coming on this very, very cold night. Andrei, you want to say something?
Yeah, I just would like to wish you Merry Christmas, seasonal greetings, and I do hope to see you again in the new year in one of our face-to-face lectures, online lectures. Very Merry Christmas.